in there now.
Okay, thank you. So here's a polynomial function of degree 5, and I'm going to try and graph it using the steps of first derivative test to determine maximums, minimums, increases, and decreases, and the second derivative test to find concavity and points of inflection. Something else that we should probably do is find x-intercepts. This particular graph doesn't have x-intercepts. You would do that by setting this equal to 0 and trying to factor it, but it doesn't factor nicely. The x-intercepts aren't that great. So if I were going to give you this question, I would provide those x-intercepts for you if you can't factor it yourself. But let's give this one a try. So the first thing we're going to do is find intervals of increase and decrease, which will allow us to find maximums and minimums. And that's done by the first derivative test. So y prime equals x to the 4th minus x cubed minus 9x squared plus 9x. So there's your first derivative. Then you want to set that equal to 0. So I'm going to set that equal to 0. And I've got to look for some factoring with this particular expression. So I created this one so it factors nicely. I see a common factor of x. Sugar. Sorry about that. Minus 9x plus 9 equals 0. Now this one you could try the factor theorem on, but actually you can group it for a common factor. So you can pull an x squared out of the first two groups, and you can pull a minus 9 out of the second two groups, and you create that world famous warm and fuzzy feeling where you've got the same grouped common factor. So we're left with this. You can do difference of squares on x minus 9, x squared minus 9, and you get 4 factors multiplied together to give you 0 for your first derivative. So that creates 4 critical numbers. X equals 0, x equals 1, x equals 3, x equals minus 3. So those are 4 critical numbers. They could turn out potentially to be maximums and minimums. We're going to make our chart in order to determine which ones are which. So make a number line here with minus 3, 0, 1, and 3. That breaks up the graph so you can see how the numbers are laid out. Now let's make our first derivative chart. X less than minus 3. X is in between 0 and minus 3. X is in between 0 and 1. X is in between 1 and 3. X is greater than 3. Now we're going to list all of our factors. Let's make that one x plus 3 and then x minus 3. Y prime is the summary column, and then what does that suggest about the function y? So let's do it column by column here. When x is less than minus 3, this is negative, but as soon as you get into here, these ones all change to positive. For this one, this is negative, negative, negative. As soon as you get past 1, it turns to positive. This one is negative and then positive all the way down. And this one is negative, 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 positive. So just remember, if we take an example of an interval here, like between 0 and 1, you take a number like 0.5 that fits into that category and you put it into each one of these columns. Well, 0.5 is a positive number, 0.5 minus 1 is a negative number, 0.5 plus 3 is a positive number, and then 0.5 minus 3 is a negative number. And so you'll get these integer signs right here. When you multiply them together, you see you get a positive for a result. And if the derivative is positive, that means the slope of the tangent line is positive. It's an increasing function. When we look at these four negatives, you get a positive for a result, increasing function. 1, 2, 3 negatives multiplied together gives you a negative for a result, decreasing function. Negative here, decreasing function. All positive factors give you a positive derivative, create an increasing function. So you see back on our number line, we're going from increasing to decreasing, increasing, decreasing, increasing. They don't always alternate, don't take that for granted, but they do in this particular case. So now we have increasing to the left of -3, decreasing to the right of -3. Increasing, decreasing means you have a maximum. Decreasing, increasing means you have a minimum. And then we look at the values. We have -3, 0, 1, and then +3. And then you need to plug these values into the original function up here to get your y values, and I've done that separately. And these are the results that I've got. You can check for yourself to see if I'm right. Substitute these values of x into the original function. So now we're going to take a look at the second derivative. And the second derivative will tell us about concavity and points of inflection. So looking at the first derivative over here, I'm going to calculate the second derivative, and y double prime equals 4x cubed minus 3x squared minus 18x plus 9. We want to take that second derivative and set it equal to 0. Well, this one can't be factored. So we would be stuck at this point to find out the critical numbers that come from that. But what I did was I typed this in on Desmos, treating this like it was just a standalone function. And when I graphed it, I found the x-intercepts. And the x-intercepts represent when y equals 0. So you're really doing the same thing here. So 4x cubed minus 3x squared minus 18x plus 9 equals 0. Couldn't factor it, graphed it on Desmos, found these critical numbers. X equals negative 2.02. X equals 0.49, x equals 2.29. So these come from, they represent really the factors of this. Not nice numbers, had to find them on Desmos. But we can still carry on after that by making a number line again for the second derivative. And now making my chart. X is less than minus 2.02. X is in between negative 2.02 and 0.49. X is in between 0.49 and 2.29. X is greater than 2.29. Now there are no factors, no columns for each factor. I couldn't factor it, so I'll just have to use one column for the whole second derivative. And then we'll say, what's the summary and what does that imply about the function? So putting a number less than minus 2.02 into this expression gives you a negative number, and then they alternate in this case, like that. So y double prime is negative, only one column, so the summary is a bit redundant. Positive, negative, positive. And that suggests about the function that you go from concave down to concave up to concave down to concave up. So concave down, concave up, concave down, concave up. And that creates points of inflection, POI, POI, POI. So the first one occurs at minus 2.02, comma, and you plug that into the original function, and you get 33.20. And you can type those in yourself in Desmos. 0.49, comma, 1.71. And then 2.29, 2.29, negative 5.71. I'm not 100% confident of my numbers there, but that's what we have. Now I'm going to graph it. I started my graph by plotting those points. I'll just set that right there and we'll finish up. So there's the graph. You can see the red points, 1, 2, 3, 4, represent the maximums and minimums from the first derivative chart, and the 3 green dots represents the points of inflection from the second derivative chart. So let's start by drawing it like this. We're going up, increasing function, we read a maximum, and then we come down to this point right here. So that's all concave down. And then from that, we switch to concave up at this point of inflection, and we reach a minimum value like that. Here's our second point of inflection in between these two, and it changes from concave up back to concave down. And then from here, concave up for the rest of the graph. So other things that we'd like to find are these 3 x-intercepts, which don't come nicely. From this function, it's hard to factor, but if we could factor it, set it equal to 0, we can find that. And that's the end of my video. I hope that helps. Have a great Easter.